Okay, I think it's time and we are online. So welcome again to Tuesday seminar series at the Warsaw Astronomical Observatory. Today we have a speaker who most of you know, Ilknur Gezer. She used to work here until very recently. Now she's a postdoc in Konkoly, but we still collaborate with each other, and the results Ilknur is going to show are actually, they came from here, but they're moving forward with Ilknur to her new job. Ilknur is originally from Turkey, did her PhD in Izmir and Belgium, and then worked in Torun before coming here, and now is in Konkoly. Ilknur, the floor is yours.
Okay, my title is as you can see, Early Recognition of Microlensing Events from the Archival Photometry, but I want to mention about the microlensing first, a bit. So gravitational microlensing methods can be used to detect objects from a mass of a planet to the mass of a star, regardless the light they emit. So when the distant star sufficiently gets aligned with the foreground compact objects, so that leads to distorted images, which is generally unresolved, and resulting with the observable magnification, as you can see in the light curve. So this is the standard microlensing event. I am sure you saw this animation many times. And when the foreground compact object aligned with the distant source star, so it produces a typical light curve. So the microlensing event used since 19th to detect a compact object, but also there are many surveys dedicated to microlensing events like MOA mostly, and OAUW and Macho. So these surveys are dedicated to microlensing events. So we are using Gaia. Gaia is also reporting microlensing events. So Gaia is the Space Observatory of European Space Agency. So it launched in 2013 and it will be operating like 2025. And Gaia is scanning the sky and it's monitoring each target like more or less 70 times. So if a object brightness rises or falls significantly, then it will be visible in Gaia. And it will be reported. And it will be reported in Gaia Science Alert System. So Gaia Science Alert System is designed for appearance in new object like supernova or unexpected light change, brightness change like cataclysmic variables or microlensing events. So I want to show some Gaia alerts here. So Gaia 20 FNR. So this is the black point that shows the time of the alert in the upper light curve. In the lower, we have another alert. But at the time of the alert, we don't know what it is. And shortly after the alert, we take spectra. As you can see, this Gaia 20 FNR shows a normal star spectra, absorption lines. It's very likely a microlensing event. We know from the spectra. In the lower light curve, we also took spectra shortly after the alert, and we saw that this is a typical classical BE star that shows a narrow absorption lines and a very strong H-alpha emission. So we know what they are, but because of spectra we have. But if we wait enough and do the photometric observations, follow-up observations, again we know what they are. We see the Gaia 20 FNR shows a typical microlensing light curve, and Gaia 19 DRP also shows a typical classical BE star light curve, shows a small increase and then goes flat. So more example, this is Gaia 18C and Z. It shows a small variation, but then it's alerted at some point. We don't know what it is. And Gaia 18 DVI also alerted. It was going up, but it's alerted a bit late actually. So again, we took the spectra shortly after the event. And Gaia 18C and Z, it shows the spectra dominated by molecular bands. So it's very likely an AGB star, evolved star. We know from the spectra. And from Gaia 18 DVI, we also get the spectra. And that's very similar to eruptive FUORI type young stellar object. Again, if we continue the follow-up, we see that Gaia 18C and Z shows long period variable variations like AGBs, MIRAs, and Gaia 18 DVI also shows the young stellar object, eruptive young stellar object light curve. So we have photometric follow-ups and spectroscopy to know what they are. But for the follow-up observations, we need to do these photometric follow-up observations to use all the network ground-based telescope. And we also need to wait until the end of the events to see the whole light curve. So another way is the spectroscopic follow-ups, but this is a bit costly and also limited to the brightness. So we are using Liverpool telescope, VLTX shooter, SALT, and mostly Gemini, GMOS North and GMOS South to get the spectra. So this is costly. We need to write proposals and we need to get the time, and it's not always possible to get time, for example, both for North and South events. So up to now, we have spectra for 86 candidate events. And for 34 events, we know the nature based on their light curve evolution. So we know 25 classical BE stars we have based on their spectra, and 20 young stellar object, 72 millisecond star or red giants, mostly the red giants, and 2 asymptotic giant branch. So this is our validation sample. So we know their nature based on either their spectra or from their light curve evolution. So the next slide shows what we did for the early recognition of microlensing event. And we already submit this work to the ANA, and actually we got quite a good positive referee report, but still in the under review. Need some iterations. So we use archival photometry. So they are Gaia alerts, but they are also mostly dusty objects like young stellar object, AGB stars, and classical BE stars. So we use 3 full sky coverage survey. And Gaia is in optical part, and 2 mass and all wise in more infrared. So in the Gaia, we have 3 bands, BP, G, RP. In the shortest band around 5,000 angstrom. And at the end of the spectrum, we have wise 4, it's 22 angstrom. So we have the whole coverage, and they're all full sky coverage surveys. But for the WISE, the WISE source identification method calls superiors, especially for WISE 3 and WISE 4. So to avoid misclassification, so we need to clean the WISE photometry first. We should be sure these WISE 3 and WISE 4 bands are real, not the superior. So this cleaning actually done by Gabor Marton in the paper. Cannot be seen now. In 2019 paper, it's a machine learning method used again. You can see in the first top panel shows the real sources in WISE 4 band, and the lower shows the superiors. So he did the binary classification using random forest to find to obtain the clean WISE catalog. So at the end, we classified totally 370 events, but none of our targets has WISE 3 and WISE 4. So we couldn't use WISE 3 and WISE 4. In the further classification, we used only WISE 1 and WISE 2. But first, we tried the traditional methods. So we plotted all possible color combinations, and these are the most diagnostic colors. In the upper panel, you can see without WISE 3 and WISE 4, those colors like K minus WISE 3, these are the most used colors also in other papers to classify youngster object and AGB stars. So there are some separations, but if we would have the WISE 3 and WISE 4, the separation would be much more clear. We couldn't use WISE 3 and WISE 4. And these are the, I don't know if you can see, these green dots are classical BE stars, reds are AGB stars, blue youngster object, and yellows main sequence stars. So what we used machine learning approach. We use the supervised machine learning method. So what is supervised machine learning method? So there are data. So we know the contaminants, like we have contaminants, classical BE star, youngster object, and AGB stars. So we took these objects from the literature, mostly from the WISE, Simbat, and Vizir. We collected we built a training sample from the known object. And then we keep like 20% of the training set as a test set. And we have experimented many machine learning classifiers like support vector machine, naive Bayes, and decision tree, and random forest. And we see that the random forest model gives the best results, so gives the best consistency when you compare with the test set. So that's the idea of the machine learning. So the random forest predicts very well the classes. So we collect all this data from Simbat and Vizir. We use several catalogs, but we classified like 370 sources, but not all of them has this 8-band photometry, all the Gaia, Tumas, and WISE. So we split our training sample in 3 cases. Then when we have 8-band photometry, Gaia, Tumas, and WISE. And the second case, when we have only Gaia and Tumas. And the last case, we have only Gaia photometry. So we did this classification for 3 different cases. So how many different classes can we distinguish with this 8-band photometry, or 6 or 3? So we calculated Pearson correlation matrix. So this is actually this Pearson correlation matrix done for the dimension reduction, because we don't want to use highly correlated features in our model. So we want to make the model simple and efficient, but we use the all color combinations for 8-band. It makes the 28 colors. And we check if the Pearson correlation coefficient is higher than 0.7 or lower than minus 0.7. But we see that for each class, different colors are useful. So at the end, we kept all the 28 colors. So we did the same when we have only Gaia and Tumas photometry. But now you can see the main giants, all the coefficients are higher than 0.7. So that means we cannot distinguish those classes with only 6-band photometry. So we combine them because they are the most common source stars in microlensing. It doesn't matter to know if it is microlensing or red giant for us actually. So we classified objects into 4 classes: U-lens, classical BE, EGB, and WISE. In the last case, again, we did the Pearson correlation matrix, and you see again, all the coefficients are higher than 0.7 for main second star, red giants, and BE star. But still, AGB star and young star objects we can recognize. So for this last case, we did binary classification. So they are either AGB or Warsaw or main second red giant or BE stars. Okay, so the less color we have, then the less classes it can be classified at the end of this. So as I mentioned already, the random forest gives the highest accuracy for the classification. These are the confusion metrics for 3 different cases. Yeah. So this is the feature importance class for random forest model. So that shows this y1 minus y2 is the most important color to recognize classes, but we cannot use for all of them, unfortunately. Okay. So now we have validation sample. I mentioned before. We know their nature based on their spectra or their light curve evolution. So we have totally 120 events that we know what they are. So we want to compare our machine learning photometric classification with this validation sample. So what we get? So we analyzed all the results in each probability threshold. So you can see the red one shows the U lens that goes up down to 85% probability. The spectroscopic classification and photometric classification are consistent. And for the young stellar object, even down to 75% probability, it's consistent with the validation sample. But for BE star, it's much more conservative, I can say, until up to 95% probability, they are consistent. This is for 6-band photometric classification. Even though we don't have voice photometry for this classification, still it's 90% probability they are consistent with the spectroscopic classifications. But since we don't have a BE star spectra for this sample, we did only for young stellar object and ULANs. So this is for 3-band classification. Okay, in 3-band classification, we did binary classification. Either they are AGB or Warsaw or ULANs and BE star, they could be. So this is the training sample plotted in BP minus G and G minus RP diagram. The cyan squares shows the Gaia alerts. And the yellow ones are classified as AGB or Warsaw. So they are not ULANs, and they are really located around the AGB and Warsaw objects. So they are very likely not microlensing event. So even this 3-band classification save time for us. So we don't need to do the photometric or spectroscopic follow-up observation for those events. So if we would have this tool before, so when I showed in the beginning, so this is Gaia 20 FNR. It's classified as a red giant in our classification, photometric classification. So we wouldn't need to get the spectra. And the same for Gaia 19 DRP. So our classification predicts also very well. So again, we wouldn't need to get the spectra. The same C and Z, Gaia 18, it's classified as AGB, and the Gaia 18 DVI also classified as Warsaw. So with this photometric classification, so we predict its 90% probability threshold, 1/3 of the microlensing event correctly. So it's save a lot of time. Actually. So we already have the web interface for this classification. So it's enough to put the right ascension and declination of your events for your alerts. This is an example. So we put the right ascension and declination. Okay, it classified as a red giant. It's very likely ULANs. And when we look at the light curve, it's already complete. It's a microlensing event. That's it. Thank you. It was so quick, actually.
Thank you very much. So we have now plenty of time for questions and discussion. Questions here, please, from the audience. Kasha.
I have a question. For example, what methods do you use as microlensing events? Because you said for YSLs and VEs you use the objects from catalogs, and for microlensing?
So I just took the main sequence stars and red giants from the Vizier catalogs.
Radek.
Could you go back to slide 32?
Yes.
Okay, so what I see on this YSO line is that when you move from 90% to 85%, which is just shifting by one beam,
Yes.
the efficiency basically drops by a factor of 2.
Yes. Yeah.
So
Yeah. This is the yes.
is it maybe caused by a small number of objects analyzed here or something? Because that's, I would say, worrying.
Yes. Yes. Actually, this 8 band, when we have Weiss, this classification is the most reliable one. So this is but
Oh, it's 6 bands only.
yeah, this is only 6 bands. So I know it drops.
Really sharp.
Yeah, sharp when we have 6 band photometry. Yeah, but still, say follow-up observation times about 90% probability.
Honestly, somehow I would be suspicious with this 90% if you use such a limit. I would not be very convinced that it's really that efficient. Somehow for me it seems questionable because there must be if you sample this curve on a finer scale, then I assume there should be some points in between. Yes. So.
Well, let me step in. There's very few examples here, right? It's a small number of statistics anyway. That's why even if you sampled it smaller beans, you would see large steps. Because we're talking about a few dozens, couple of dozens of cases. That's why it's limited.
So that's the reason.
Yes. With a larger verification sample, and we have the verification sample of 120 targets, which we then split into these 3 classifiers and then into subclasses. So we're left with a small number of cases.
2 more questions.
Yeah.
One is, so you consider YSOs, VE, and AGP stars as false positives for microlensing. Are these, so I guess you have not considered CVs in general, cataclysmic variables.
Yeah, no. Yeah, but series is short variables. It can be seen quickly.
Okay, are there any other astrophysical false positives that you...
So these are the most we encounter when we got the spectra.
Okay.
Well, also, if you restrict yourself to the galactic plane, you get rid of most of CVs. And somewhat there were not too many. Yeah, well, you do see CVs there, but as Ilknur said, they have shorter timescales quite often, and Gaia misses them because of the cadence. And literally, we had like 1 or 2, no more, in the sample. So we thought it's a negligible contaminant.
Okay, so final thing. So you use the limit on this Pearson coefficient of 0.7.
Yeah, this is it.
Does it come from anywhere, or is just made up number that is?
No. It's the common limit which is used for the Pearson collisions. So I have the reference also in the paper where these numbers come from.
Okay, thank you.
Thank you, Radek. Shall please?
Have you thought about including more information about the objects in the classifier? For example, have you thought about including the likely information, the data points themselves? in the classifier to improve the classification. I think that the shapes of these outbursts of B-type stars are different from those of microlensing events because the timescales are a bit different.
Yeah, but we wanted to make a tool completely independent from light curve and the
kind of to make it survey,
yes,
not depending on the survey. So
Yes.
essentially, because then you go into details. Okay, this is the survey with the given cadence, and different surveys will have different cadences, so different information. And also, if you show the very first example, over there you have flat light curve and a point in both cases. So you can't tell them apart actually. We thought about this, of course,
Yes.
to include this information is there, and they were papers like this done by other people.
this one.
Actually, yeah. If you look here, one slide earlier, actually, when you cover, the bits. Okay, I agree. There is some, yes, yes. Sure, but that's a different classifier. Yeah, that would improve for sure.
Yes.
But we're trying to stay away from any survey-specific characteristics, which would limit you, right? In that sense, now you just enter the coordinates from any survey, and you don't need to worry about cadences and stuff like this, limits, noise, and scatter, and so on. But of course, that would improve.
Yeah.
It's not a perfect classifier, as you can
Yes,
see, it
yes.
drops dramatically.
Yeah.
But in many cases, it would have saved a lot of time if we have had this before. It's a complex grammatical sentence.
And it would be better, for example, to use Spitzer, but it's not a full sky, so it makes the sample smaller and smaller. For only a few events have these IRAC photometry, for example. So we want to make this some general tools. So.
Any more questions and comments?
I might have missed it, but do you correct for reddening the bright colors in another way?
But we use only colors. We didn't use brightening.
But still colors change with reddening
Yeah.
in the optical.
Yes.
So you don't.
We
Correct.
didn't do such things.
So wouldn't you worry this would be more reliable only for closer objects?
Yes. This is actually the comments, one of the comments of referee. So we will.
Maybe Christian was there.
Yes. Yes, we will do this.
But of course, as Ilknur has shown, that the infrared bands, they carry most of the information, and you're less affected
So
by
why
it.
would Gaia at one?
But in some cases, you only have Gaia. That's all you have. So for some subset of the targets, we can only rely on Gaia. But it's not perfect. We wish we had Ys for all the sky, but it has gaps, right? That would be perfect to have the whole sky deep, complete infrared survey, right? If you know one, then let us know. Any other comments from here? I have to check if there are comments on Zoom. I don't see any. Any comments, any questions from Zoom, people? No. Okay, so if there are no more questions, so let's thank our speaker again. And we can have more cake.